Hi, Cal again here with section 16.3, the fundamental theorem for line integrals, and 16.4, Green's theorem. I apologize, I'm short on time, so I'm doing this one blind. So this might be a little rockier than usual. Alright, the main result for section 16.3 is theorem 2 right here. If I have a gradient vector field, if big F is equal to the gradient of little f for some function, little f for some potential function, recalling section 16.1, then I can calculate a line integral along any curve of that vector field very easily. It's just f of the ending endpoint minus f of the starting endpoint. This is really, really important. If I have a conservative vector field, if I have a gradient vector field, then the path along which I get from A to B doesn't matter. The curve doesn't matter. Only what the two endpoints are does matter. So conservative vector fields are clearly very special. And so, yeah. You don't have to worry about the proof of the theorem. Example 1 is fantastic. And you do want to read carefully this blurb about independence of path. And about closed curves. And what happens with a line integral for a conservative vector field on a closed curve. Theorem 3 it's important, but I would kind of think of this the other way around. If I know that my line integrals are independent of path, then I know that the line integral of f is going to be 0 along every closed path. Theorem 4 says that if a vector field is independent of path, then f is a conservative vector field. It has a potential function. And again, I usually think of this the other way around. If f is a potential function, if f is a gradient vector field, if it's a conservative vector field, then line integrals of it are independent of path, which can be really useful. Okay, don't worry about the proof. You should be familiar with theorem 5, which is another important idea along these lines. You should be familiar with the concepts of simple curves, of simply connected regions, and the theorem that we have for that to tell when f is conservative. I would work pretty carefully through the next 3 examples. And I would work through example 5 about finding the potential function once I know that a vector field is conservative. Then we get into a discussion of conservation of energy. I am not so bothered by this as some people will be. The physicists might be pretty interested, so you might want to read that. And that ties together 16.3. Moving straight into 16.4 is Green's theorem. And what Green's theorem says is that first it establishes the idea of a positive orientation of a curve. It's just that we want to go around, if I have a curve that encloses a region, we say that we have positive orientation on that curve if I go around it counterclockwise. And what Green's theorem says is that if I have a simple closed curve, which is piecewise smooth, and if it's positively oriented, if I traverse it counterclockwise as I go around a parameterization of the curve. And if P and Q have continuous partial derivatives on an open region containing D, the enclosed region, then the line integral around the boundary of P dx plus Q dy, well, that's the same thing as F dot dr, is the double integral of dq dx minus dp dy with respect to area over d. So what Green's theorem lets you do is it lets you turn a line integral around a closed curve into a double integral around the region that that closed curve encloses. This is an extremely important theorem, and we're going to have a couple more like it later in the chapter. And the important thing here is that this links a line integral, which is kind of tough to deal with a double integral, which is not so hard to deal with. Or if you have a double integral with a really tough region, but maybe the line integral for it, maybe the curve isn't so bad, then it makes it easier this way as well. Moving onward, you don't really have to pay attention to the proof of Green's theorem. I would read the examples in this section pretty carefully. So example 1 is good to work through. Example 2 is good to work through. And I would read the blurb on the bottom of 1110 about another application. We can also use this to find formulas for areas of a region based on line integrals of the bounding curve for the region. That can be an important thing. And so example 3 gives us an application of that idea. I wouldn't worry too much about a planimeter, and I wouldn't worry too terribly much about extended. Well, the extended versions of Green's theorem, you might want to give a quick read. They're useful. So do read that. Read through example 4, example 5. But I'm more concerned that you basically know what Green's theorem says and how to use it in simple areas. So that's all I've got for these two sections.